Hello, we come to part C, the third lesson of this unit. And here we're continuing to discuss sort of aspects of the big data classification I introduced. And in this little lesson, we will discuss some slightly cosmic issues concerning clouds and HPC and the relationship of simulation applications, so-called computational science, and data science and data analysis applications. So first, clouds and HPC. Quite a controversial subject, though I think the answer is relatively clear. All right, so if we look at cloud computing, which of course underlies our class, then we have various aspects of it. A lot of the important aspects are connected with the business model, the fact that you outsource servers, you convert capital expenses into ongoing outlays, and Azure and Amazon and things exemplify that. And the other aspects of clouds are the so-called platform or the runtime. These are the tools that do data parallel computations. They're actually valid on clouds and traditional clusters. They're not, apart from those that actually implement hypervisors and virtual machines, they're not particularly dependent on virtualization. They run Hadoop, for example, runs equally well on virtual machines as it does on bare metal without any hypervisor. And of course, these are the Google's MapReduce, Microsoft's Dryad, which is now no longer available, Bigtable, Chubby, that's Zookeeper and Apache. These are all examples of really remarkable tools that were introduced with clouds. However, they really weren't associated with clouds. They were more associated with the need to have these tools that they're more big data specific than cloud specific. So as we've mentioned, MapReduce was a brilliant system designed for information retrieval and recommender engines and things like that. It's excellent for a wide range of science data analysis, especially if you extend it to do iterative problems. So that's what it says here. We can do much traditional parallel computing if we do iteration. And in the previous lesson, we talked about map communication, which was done by Giraffe, and map collective, which is what Spark and say the original Twister did. Then we have another feature of the cloud infrastructure is data parallel file systems, HDFS and Bigtable, and that contrasted with wide area file systems like NFS, Lustre, and things like that. And then the whole thing is captured in this Apache Big Data Stack underlying this whole course. So now let's put this all together in this as a service diagram. At the bottom, we have network as a service, OpenFlow, Genie, software-defined networks. This is likely to grow in importance as it allows you to dynamically configure the networking. Here we have infrastructure as a service built on top of network as a service. That's where we have bare metal or OpenStack, Eucalyptus, OpenNebula, CloudStack. These are currently probably the dominant ones. I think Nimbus is merging with OpenStack. Eucalyptus is still going there, but it's not quite as important as it used to be. Then we have on top of infrastructure as a service, the middleware, which is characterized by being applicable to many different applications. So we have MapReduce. We have libraries like PETSI and Saga in high-performance computing. We have compiler tools, SensorNet tools, monitors, and things like that. Then we have software as a service, which can run in education, applications, maybe CS research use for these particular classes, test a new way of doing storage. And this sort of four-layer model is valid universally and highlights the fact that clouds have introduced the software at this level, especially here, which has enabled us to build the rich big data software as a service. So if we look at science computing environments, they used to consist of very large-scale supercomputers. In fact, it still consists of very large-scale supercomputers. These are multi-core nodes linked by a very high-performance, low-latency network. Often now we have a GPU or Intel Phi enhancements, accelerators, and they're suitable for highly parallel simulations. Now, another important aspect of the science environment is so-called high-throughput systems, such as in the US, the Open Science Grid, or in Europe, the European Grid Initiative. And those are aimed at those pleasingly parallel jobs, which, as we noted, was maybe at least a half the applications in this survey. One of the ways of doing this is to do cycle scaling, where these pleasingly parallel jobs hide in computers and pop up when they're idle. And the LHC data analysis is an example of a pleasingly parallel problem. Then we have in science, of course, from sort of early 2000s till 2010, grids were dominant. They federate resources and enable convenient access to multiple backends, such as lots of supercomputers. Grids allow you to run on any one of those supercomputers with a given environment. All of these approaches use services. So a service-oriented architecture is compatible with all of these. Essentially, all of them can use portals, which is the user interface, and all of them can use workflow, which integrates multiple processes or applications into a single job. So if we look at the three sort of things we saw, clouds, high-performance computing, supercomputing, and grids, then we have this sort of important inequality. The grids have more synchronization overhead and lower communication capabilities than clouds, and clouds have more synchronization overhead and lower communication bandwidth than classic HPC systems. So this says clouds will execute essentially all grid workflows, but they're not so clearly implement. They cannot so easy to implement. Some closely coupled. They can do some HPC applications, but if those HPC applications really need the really highest performance communication and lowest synchronization cost, then you want to spend the extra money to build a very tightly coupled supercomputer. And so, HPC machines, or which we can call MPI engines, they offer the highest possible performance on very closely coupled problems. And now we come back to the four forms of MapReduce. Map only, that's grids and clouds, and of course, in fact, everything. Classic MapReduce, which is not so obvious, it runs well on grids. There are some MapReducers that can run in distributed fashion. It all depends on some aspects of the architecture. Often they can be done in the distributed fashion. And iterative MapReduce, that will not run well. That will run well on clouds, but not run well on grids because it has a synchronization between the iterations, between the different iterations, which require relatively high performance. And then the fourth architecture is classic MPI, point-to-point messages, PDE solvers, and of course, as we noted, those are also graph algorithms. So in some sense, if you want to get the most cost-effective solution, you use the system with the minimum required synchronization. And of course, grids have the highest synchronization cost, or they support the least synchronization as they're distributed. Clouds has MapReduce, which are typically write to disk, which is relatively high overhead, and and the results are saved on disk, which gives you fault tolerance, but has this say synchronization overhead. The reduce integrates the results from the different maps. Say the key feature of this is fault tolerance, used in search and recommender engines, and has the map only special case. Iterative MapReduce caches results. It runs quite well on clouds, and it supports the classic single program multiple data parallel computing model with large messages which are seen parallel linear algebra. You get that in clustering and multidimensional scaling, etc. High performance computing is also always single program, essentially always single program multiple data. The maps are now processing particles on mesh points, and there are lots of low latency messaging often needed, and you need specialized networks like InfiniBand and technologies like MPI. Here you often run very large jobs, are going up to 1.5 million cores on a single job. The machines supporting it run at 100% utilization, so they're very effective use. They're rather fragile fault-wise, and they can't tolerate things like outlier maps, because when you have a giant parallel job with a million cores, if one core is slow, the other million minus one cores all have to wait for it. So you actually have a huge slowdown. Any one core slowing down slows down a million cores. So in spite of that, I would note that although they're very important HPC machines, they're often used unnecessarily because you could get by with lower synchronization cost. So we can look at when and where HPC is most important in this integrated architecture. We've noticed resource management, Yarn v. Slurm. We've noted file management, IRODs. We've noticed programming, where HPC has extensive parallel computing expertise. We've noted communication, where MPI has looked at all sorts of different networks and found the best way of doing communication. It seems clear we should reuse that in ABDS. Monitoring, a lot of those come from HPC, and workflow has several entries from grid computing. So these are the key layers for HPC Apache Big Data System integration. In the last part of this lesson, we will compare data-intensive and simulation problems in 3 slides. Pleasingly parallel is common in both cases. Both of them use single program multiple data. Big data, when it's iterative, or actually even also the graph problems, is typically what's called bulk synchronous processing. I used to call that loosely synchronous, but that name didn't take off. We have the streaming event style, which is very important in big data, but not so important for simulations. You start seeing something like that when maybe you're doing so-called parameter sweeps and running over a set of parameter values, but that really has not got the same streaming structure that is, say, present in the Internet of Things applications. Ordinary MapReduce is a dominant big data paradigm because it's so important in search and recommender engines. This is not a common simulation paradigm, except when the reduce summarizes a lot of pleasingly parallel executions, say as in the Large Hadron Collider, where you might analyze each of the events independently and then sum up lots of histograms or statistics over all the events, which will be the reduce phase. We noted there are many big data algorithms who have large collective communication, whereas classic simulation is small point-to-point messaging. Simulation is dominantly sparse, coming from the nearest neighbor, from either short-range forces for particles, or from when you take a differential operator and approximate it numerically, you always get differences of nearby points, and that gives you sparse structure, which really has no analogy in the big data problem. I don't think big data ever sees that type of, let's numerically approximate a differential operator and get some sparse structure from that. It has sparse structure, as in things like bags of world algorithms, where you have a bunch of rankings and things like that, because a given user only ranks a few of the items that you're looking at, a few of the movies or books or what have you. Related to this, data analytics often involves full matrix algorithms, or sometimes banded full matrix, as in the case of deep learning, whereas you do rarely see full matrices in the simulation case. You can actually, as we see on the next slide, find similarities between graph problems and particle simulations with a strange cutoff force, where the connection between the points in the graph, that with maybe, let's say it has a strength W, that corresponds to a force or a potential of that same strength. And so the points connected in the graph correspond to the particles that have a mutual force between them. Each of these is implemented and architecturally as map communication. Another very interesting point is the large number of big data problems that map into the long-range force because all points are linked. If you take gene sequences, or you can calculate the verticom as the distance or between or the alignment of any two gene sequences, and that can be converted into a distance between those sequences. So all sequences have a distance to all other sequences. Long-range force problems are well known to be the easiest to parallelize. They're often full matrix algorithms, where in the case of the sequence analysis, as I was discussing, the distance is defined by programs like BLAST or algorithms like Smith-Waterman. And this is a little out of scope for this talk, but there's lots of very interesting research to be done in taking long-range force algorithms for big data and making them run faster, because long-range force tends to be order n squared. It'd be good to convert them to order n log n, and there's some clever methods that allow that to do. I mentioned here full matrices. In the case of deep learning, you get block sparse. So that's actually operationally full matrices, although the matrix itself is actually sparse. Because the way you build a neural net, it's designed to be sparse. But it's locally, it's full. So that it actually looks like a full matrix algorithm in terms of the nature of its performance model and the algorithms, the software it needs. It's interesting that conjugate gradient appears to be very important in big data, but at least when I use it, it's for non-sparse matrices, whereas in the case of simulation world, they're looking at sparse conjugate gradient. So that's another example of this interesting difference in sparseness between big data and simulations. So here is this diagram which basically compares. Here we have the particles linked in some chemically with chemical bonds representing the forces between the particles. And now we have here, over here, the points are no longer molecules, they are actually people, and you have people connected here. Here's a very friendly me connected a bunch of people who lie in clusters. So you can see these, each of these pictures, if you want to try to simulate it or describe it, is a set of points, molecules, people, and then you have a specification of the connection between those points. And so there's clearly some important similarities between particle dynamics algorithms and the graph algorithm that you get in many big data problems. So what have we done in this whole unit, which had 3 lessons? We described SQL and NoSQL. We discussed the various forms of MapReduce, the 4 forms. Those were both software and machine architectures. We discussed the relationships of clouds and high-performance computing and big data and simulations. And we had an example of global machine learning, which is sometimes called exascale global optimization, which is particularly challenging. Thank you very much. In the next unit now, this is the end of this unit. This is the unit on features. The next unit will actually discuss particular application areas, especially from the NIST Big Data Study. Thank you very much indeed.